So today we are going to mostly focus on DC biasing of NMOS circuits, but in order for us to do that, I want to first introduce the schematic symbol for an NMOS capacitor. Actually, I think I'm going to introduce three of them. We're only actually going to use one in this class. We're going to talk about the large signal model for NMOS capacitors. And why we are effectively not going to actually be able to use it to do anything. And then we'll get into our DC biasing networks, okay? So schematic representation first. So we know that an NMOS transistor is a 4-terminal device. And typically speaking, the drain terminal is at the highest potential. We're going to put our gate terminal over here, and I want to actually delete that. We're going to put our source terminal down here. And this guy in the middle will be our body terminal, okay? And for an NMOS transistor, the arrow points out towards the body terminal. Our drain current is defined to be in this direction. So it flows from the drain to the source, which may seem odd because the source is what's really supplying charge carriers for this device. But because for an NMOS transistor, the source is supplying electrons, and we know that the current should flow in the opposite direction of electron flow, it makes sense that the current flows from the drain to the source. And also it makes sense because the drain is the position of highest potential. The source is typically the position of lowest electrical potential. And so it absolutely makes sense for the drain current to flow from high potential to low potential. Okay. So this is the kind of classical schematic representation. One thing that I want to point out here, it looks kind of similar to a BJT, but there is a little space between the gate terminal and then the bulk and everything. What that's trying to represent is effectively the gate capacitance of the device. We should observe that there will never be a current IG flowing into or out of the gate terminal for a DC biasing situation. There may be gate current in our small signal analysis, which is what we're going to do with amplifiers, but that's really dependent on what frequency we're operating at, because we know that the impedance of the capacitor is not infinite for certain angular frequencies, right? As frequency increases, the impedance of the capacitor goes down and it starts behaving more and more like a short circuit. So depending on what frequency we're operating at for our small signal analysis, we might have a gate current. But with regards to DC, we should never see a gate current. Another representation that is very commonly used is this guy. We still have our drain. Still have our source. Here is our gate. And then we have effectively tied the body and source terminals together. Okay. This is done when effectively we either want to or can ignore body effects and the body effect on the change in the threshold voltage. So if the body and the source are at the same potential, body effect is exactly 0. And we'll go from there. And then finally, our drain current will still be this guy here, ID. And then from there becomes the simplest representation, which makes our transistor look like a 3-terminal device. Here's our drain. arrow. That's our source. This guy is our gate. And there's our drain pad. So the arrow pointed out tells us that it's an NMOS transistor when we're using the 3-terminal representation. This is the one that we're going to be using in this class the overwhelming majority of the time. Okay, so I wanted to introduce you to the others because it may pop up every now and then, but for the overwhelming majority of analysis that we're going to do, we're going to use the simplified 3-terminal representation with the understanding that the body and source are tied together so that we do not have to include any body effects in our analysis. All right. Any questions on these 3 different ways we represent things? Kind of, it is what it is, so I don't know what kind of question you might ask, but anyway. All right, so now let's talk about our large signal models. So large signal models are our DC models, okay? And they're going to look something like this. Here we're going to have our gate terminal. Down here will be our source terminal. And then over here will be our drain terminal. And we'll do the saturation one first. So for our saturation model, between our gate and our source, we see the gate oxide capacitance. So it's literally going to be an open circuit over which a voltage VGS appears. Okay. This voltage VGS controls the amount of drain current that flows through the device. So between our drain and our source, we are going to place a dependent current source where this current has a value of 1/2 VGS minus VTH. Sorry, I forgot a couple of things here, so we'll get to that in a second. 1/2 mu n Cox W over L VGS minus VTH quantity squared. And when channel length modulation effects are present, there will also be a 1 plus lambda VDS term. And I'm going to introduce something new here. I want to call this quantity mu n Cox W over L K sub n. K sub n is what's known as a transconductance parameter. So effectively, it's just telling us how efficiently this device converts that voltage into a current. And when we talk about small signal models, it's going to play a role as well. Yeah, it can be, so between 0 and 1 means it either doesn't convert or it only converts on a 1-to-1 ratio. But the ratio that it converts is dependent on the electron mobility, the oxide capacitance, and the aspect ratio. So it can, typically speaking, we're talking about values somewhere between 100 microamps per volt squared to a couple of milliamps per volt squared. Okay. So this is our transconductance parameter. And really, it just saves us from having to write that crap over and over and over again. So this red portion is here representing what happens when channel length modulation effects are present. So I'll write something there too. CLM include. And I want to introduce a slightly different version of the transconductance parameter, Kn prime, which is simply Kn divided by W over L, or the aspect ratio of the transistor. Okay. So the reason why this symbol is introduced is because if we were developing an integrated circuit using MOSFET transistors, it's very likely that all of them will have the exact same Kn prime value because they're all being fabricated on the exact same substrate using the exact same process. So mu n and Cox will be the same, but we want to be able to have different aspect ratios or different sizes of transistors to achieve different currents. So this is what this Kn prime gets used for. Okay. So for discrete devices, we're probably going to define things in terms of this. For integrated circuit based devices, we'll probably use this guy. Okay. All right, so this is what our large signal saturation model looks like. Between our gate and our source, we have an open circuit representing the gate oxide capacitance. Between our drain and source, we have a voltage controlled current source because that's exactly what the transistor does. Converts a voltage at the input into a current at the output. For our triode model, we're going to start with the same thing. Just a set of terminals, and then talk about what should occur between all of them. So what do you think should happen, or what do you think should be between the gate and source in the triode region? Does the gate act any less like a capacitor when there's less current flowing through the device? No. So we're still going to have some voltage VGS. We know that in the triode region, there is a current flowing from the drain to the source having a value of mu n Cox W over L times the quantity VGS minus VTH times VDS minus 1/2 VDS squared. I'm going to write that down in a second. So effectively, what we're going to have is another dependent current source. It's just going to supply a different amount of dependent current. VGS minus VTH, VDS minus 1/2 VDS squared, or Kn VGS minus VTH, VDS minus 1/2 VDS squared, and VDS is just the voltage drop between the drain and the source here in both cases. Will I have a channel length modulation term ever for my triode region operation? No. Channel length modulation means that we are operating where our channel is pinched off, which is only true when we are in saturation. So this is what we're going to have. So it should be pretty obvious why actually representing our transistor with the large signal model isn't particularly helpful when both of our large signal models are identical. They're both a capacitor and a dependent current source. How do we know which one of the two models to use? Well, the short answer is we don't. And that's what's going to bring us into our DC analysis portion. Okay. a MOSFET, DC biasing, NMOS in particular. We're only going to have two circuits that we need to analyze, okay? So the first one that we're going to analyze is called the 4 resistor bias network. And first, we're going to look at it with channel length modulation not included to make things a little bit easier. So this is the most common biasing network that is utilized, and it is effectively what I called a full bias network for BJTs, just using an NMOS. So we're going to have some resistor R1, some resistor R2, a resistor between the source and ground, which we'll call RS, a resistance between VDD, our power supply voltage, and the drain, which I'm going to call RD. And just for the sake of argument, we're going to label our terminals G, D, and S, and our quantities that we need to solve for, ID, VGS, and VDS. So let me ask you guys a question here. Is there anything about this drawing, this schematic representation, that tells us anything about the mode, so either cutoff, triode, or saturation, at which this device is operating? Not really, right? The only thing that I can say is that if VDD were less than our threshold voltage, we're probably operating in the cutoff region. That's the only thing that I can say based on the schematic representation alone. Okay. So we are going to have to make an assumption. We're either going to have to assume that the device is operating in the triode region and either prove that assumption right or wrong, or we're going to have to make an assumption that the device is operating in the saturation region and then prove that that assumption is either right or wrong. As it turns out, the analysis for the saturation region is a little bit easier because there's only one unknown quantity, VGS, right? So we don't have a dependence on both VGS and VDS simultaneously. So we're going to start by assuming that the device is operating in saturation mode. Okay. So assuming saturation mode operation, we know that our drain current, ID, is equal to 1/2 mu n Cox W over L VGS minus VTH quantity squared, or 1/2 K sub n VGS minus VTH squared. So we currently have two unknowns effectively, okay? ID is a quantity we don't know. VGS is a quantity we don't know. So we can figure out what at least a part of VGS is. What I mean by that, VGS by definition will be the voltage present at the gate terminal minus the voltage present at the source terminal. And we can pretty easily see what the voltage present at the gate terminal is because we know that there is no gate current IG. So the left-hand side of this circuit is just a simple voltage divider 100% of the time. And so that tells us that VG is equal to VDD times R2 over R1 plus R2. Everybody okay with that? So what we're going to do now is we are going to do or perform Kirchhoff's voltage law around this bottom half loop, right? Because we could start at ground and end at ground, and that's a complete loop. And so hopefully we should be able to see that VG, the voltage drop over resistor R2, is simply VGS plus the voltage drop over resistor RS. Oops, my apologies. So using KVL, we have VG is equal to VGS plus ID times RS. And we can do a little bit of algebraic manipulation to find that ID is VG minus VGS over RS, or VDD times R2 over R1 plus R2 minus VGS, all multiplied by a factor of 1 over RS. Anybody have any beef with my algebra here? All right, so we have an expression for ID in terms of VGS. We have a second expression for ID in terms of VGS. So we're going to equate those two relationships and then do some algebra. Okay. So if I equate my two relationships, I'm going to have VDD times R2 over R1 plus R2 minus VGS, all multiplied by 1 over RS, is equal to 1/2 K sub N VGS minus VTH squared. What I'm going to do now is I'm going to expand this squared thing. I'm just going to FOIL it. I'm going to multiply both sides through by a factor of RS, and I'm going to put effectively 0 on one side of the equal sign. And so by expanding this and rearranging, what we find is we'll get 1/2 Kn RS VGS squared plus 1 minus Kn RS VTH times VGS plus 1/2 Kn RS VTH squared minus VDD times R2 over R1 plus R2 equal to 0. This is a second order polynomial of VGS. It's a quadratic function. It has some nasty looking coefficients for sure, but it's a quadratic function, okay? So we can call this guy right here A, this guy right here B, and this guy right here C. And using our good old 8th grade math, say that VGS is equal to negative B plus or minus B squared minus 4AC all over 2A. Let's talk about this result for just a moment. All right, so the overwhelming majority of the time, the quantity B is going to be negative. Unless Kn is very, very small, B is going to be a negative quantity. And so negative B is going to be a positive quantity, okay? So we're going to have some positive quantity plus or minus this guy right here, okay? B squared has to be a positive quantity. A has to be a positive quantity. C, hit or miss, okay? What's going to happen is that the negative solution of this guy is effectively always going to give us a negative value for VGS. What's wrong with that?
Have our circuit operating opposite.
So what are the conditions for our device to be on? VGS needs to be greater than VTH. If VGS is negative, that's a problem, right? So the second solution, the negative solution to this guy, we're going to throw away. It's going to be wrong. I can't say that it's 100% of the time because I haven't really done the math, but 99.999% of the time, the negative solution is not helpful, okay? So with the positive solution, and so many common terms throughout this thing, I actually suffered through the algebra, and we can find that VGS reduces to VTH minus 1 over KNRS plus the square root of 1 over KNRS quantity squared plus 2 over KNRS VDD times R2 over R1 plus R2 minus VTH. I have not yet found a case in which this solution does not provide a VGS value that is both positive and larger than VTH, but I have not tried every possible combination of numbers, obviously, because that can't be done. So we are going to call this our solution for VGS. Once we know VGS, which is just based entirely on our circuit parameters here, we can then calculate the value of ID using the relationship Kn, 1/2 Kn VGS minus VTH squared. So how do we verify that our assumption of saturation mode operation is correct. Anybody have any thoughts? Anybody remember what the constraint for saturation mode operation is? The first one is that VGS needs to be greater than VTH so that the device is on and able to conduct. What was the second one, Abdullah? Or what, were you just saying something, or did I mishear? I'm sorry. Okay.
The VDD has to be less than V.
Yeah.
Oh, that's the cutoff.
Yeah. Absolutely correct. VDS needs to be greater than or equal to VGS minus VTH for this guy to be operating in the saturation region, okay? So let me scroll up here real quick. Obviously, we know a means by which to calculate the quantity VGS. Subtracting VTH from that should be fairly trivial. Now we need to figure out how to determine the quantity VDS. So let's look at our graph here, or let's look at our schematic. VDS is going to be VDD minus the voltage drop over RD minus the voltage drop over RS if we do KVL on the right-hand side of the circuit, right? Seems fairly obvious that a current of ID flows through the resistor RD. But what's the current that flows through resistor RS? We actually already used it, and I didn't explain why we could use it. Nobody caught me on it. IP, yeah. Why is ID flowing through RS? Because there's no current branching off from the gate or anything like that, right? So this isn't a BJT. We don't have to worry about the sum of these two currents because one of them is always zero. So ID flows through the right-hand side of the circuit 100% of the time. All right, so from that, VDS is equal to VDD minus, and I'm just going to lump these guys together, RD plus RS times ID. If I'm going to put two F's here to get the what I think is the computer science language of if and only if, maybe that's a mathematical representation. If and only if VDS is greater than or equal to the quantity VGS minus VTH, are we done, right? It could work out that we do all of this work and find that VDS is less than VGS minus VTH, which means our device wasn't operating in the saturation mode region, and we have to completely start over and analyze it in the triode region. So before we go through that analysis, I would highly suggest that you guys do what I have done and make a little MathCAD worksheet that literally has these relationships, right? So that you can easily calculate these quantities and see whether or not that's the case, instead of having to do all of that work by hand. So on an exam, and we'll find out why in a moment, on an exam, a question I might ask you would be like, assuming saturation mode operation, analyze this circuit and tell me whether that assumption was correct, okay? If the assumption was correct, then determine the DC operating point of the device or something like that, okay? Because we're going to find that in the triode region of operation, the system of equations that we're going to get is going to be two equations, two unknowns, but both of them have second-degree polynomial-based relationships, which means your calculators literally can't solve it. Your computers can for sure, very, very trivially. But your calculators will be crap out of luck. So triode region operation determining the DC operating point requires the use of computer algebra tools. Okay. All right. So if and only if VDS is greater than VGS minus VTH, are we finished? All right, so let's look at this guy, assuming triode region operation. So in triode region, we know that our value of ID is changed. It should be mu n Cox W over L VGS minus VTH multiplied by VDS minus 1/2 VDS squared. I need to open my bracket over here. Our value of VG obviously doesn't change at all. Won't change for any of the analysis that we'll do here. So we can see doing KVL around that bottom loop, VGS is equal to VG minus ID times RS. I'm just going to scroll up here so we can see that, prove it pretty easily. So we said that VG was equal to VGS plus ID RS. So it stands to reason that then VGS is VG minus ID RS, which is just what I said. And substituting in our relationship for VG and our relationship for ID, we get VDD times R2 over R1 plus R2 minus K sub n RS VGS minus VTH VDS minus 1/2 VDS squared is our first equation, right? VGS here, okay. If we write a KVL equation on the right-hand side, this is the exact same VDS equation we got just a moment ago. We find that VDS is equal to VDD minus RD plus RS times ID, and substituting in our equation for ID, this becomes VDD minus KN RD plus RS multiplied by VGS minus VTH times VDS minus 1/2 VDS squared. Because of the second degree polynomial relationships here, we're actually going to, when we solve this system of equations, there are two possible solutions. Okay? Only one of the solutions will satisfy the constraint that VDS is less than VGS minus VTH, which means we have correctly assumed triode region operation. Okay. Unfortunately, these guys can't really simplify down any further, so that's why I'm telling you, you need to use a computer algebra tool to solve this set. And it's important as to what, if you're using MathCAD anyway. So if you throw this equation in a solve block in MathCAD, you tell it to find VGS and VDS, it's only going to return one of the two possible solutions. And the solution that it returns is dependent upon the guess values that you put in. for VDS and VGS. So I would argue that your guess value for VDS should be at least VTH lower than your guess value for VGS, since you want the result that gives you triode region operation, right? So we can try to force that by setting up the system where it starts its iterative process in the triode region and hope that it resolves that way over time.
You repeat that? What did you say? How much lower?
VTH.
Or like what should be lower?
VDS should be at least VTH lower than your guess value for VGS. Because triode region of operation says that VDS needs to be less than VGS minus VTH. Okay. So typically speaking, I would say VGS is 1, VDS is 0, and for the overwhelming majority of NMOS transistors where VTH is less than 1 volt, that's good enough to get the answer correct. All right, so we have 30 minutes remaining. Do we want to work a numerical example or no? Okay, it would be nice. Let's do it. All right, so let's say that we have the following circuit. A 4 kilo ohm resistor, 10 kilo ohm resistor, $500 ohm resistor down here, 3.5 kilo ohm resistor here, a supply voltage of 1.8 volts, and we are told Kn is 1 milliamp per volt squared. Our threshold voltage is 0.4 volts. And our channel length modulation coefficient of lambda is 0 per volt. So that we know we can use the equations that we've just developed because we are neglecting the effects of channel length modulation. Okay. These are the only parameters that we need to work with, okay? So we would start by assuming saturation region operation. In which case we know that VGS is equal to VTH minus 1 over Kn Rs plus the square root of 1 over Kn Rs quantity squared plus 2 over Kn Rs times VDD R2 over R1 plus R2 minus VTH. And if we plug these values in, so obviously here R1 is 4 kilo ohms, R2 is 10 kilo ohms, and Rs is 500 ohms. We wind up getting 1.146 volts. Obviously, this is greater than VTH, so we're at least at a reasonable start. Okay. From here, I could then determine VGS minus VTH, which would be 0.746 volts. Okay. I could then determine ID 1/2 Kn VGS minus VTH quantity squared, which would yield a result of 278.576 microamperes. And using this value of ID, I could turn VDS as VDD minus RD plus RS times ID, which would yield a result of 0.686 volts. No, I didn't give you guys enough time to really throw this in your calculator and verify anything, but this is what my MathCAD sheet gave me, so I'm sticking with it. So, Jacob, is our assumption of saturation region operation correct? I disagree. For saturation region operation, VDS 0.686 volts needs to be greater than or equal to VGS minus VTH. 0.686 is less than 0.746, so we were wrong. Is that clear? Okay, because you're gonna have to do this literally every damn time. So it needs to make sense as to why we're saying we were incorrect. So, oops, I don't know what, well, okay, it came back. Now, we would have to rework the problem, assuming triode region operation. Luckily, we can just go to the equations that we've developed. So our first equation, VGS is VDD times R2 over R1 plus R2 minus KN RS VGS minus VTH, VDS minus 1/2 VDS squared. Our second equation is VDS is equal to VDD minus KN RD plus RS VGS minus VTH multiplied by VDS minus 1/2 VDS squared. And when we solve, we get two solutions. The first solution says that VGS is 1.147 volts and VDS is 0.690 volts. The second solution is VGS is equal to 1.278 volts and VDS is 1.738 volts. Which one's correct? Raise your hand if you think it's solution one. See, 3 people. Raise your hand if you think it's solution 2. See, like 7 or 8 people. It's 1. Yeah, it has to be 1. VDS needs to be less than VGS minus VTH for this device to be operating in the triode region. Solution 2, if VDS is greater than VGS, it's definitely not less than VGS minus something else, right? So solution 1 is the correct relationship here. Now that we know which one to use, we would plug these values in to our relationship for ID, Kn, VGS minus VTH times VDS minus 1/2 VDS squared. And we would find that we get a current of 277.408 microamperes. So just to reiterate, let me scroll up here. We decided that we were not finished with the problem after assuming saturation mode operation because our numerical value for VDS was less than our numerical value for VGS minus VTH, which cannot be true in the saturation mode operation. So that's why we tried triode. In triode, we got two solutions, one of which gives us a VDS value that is less than VGS minus VTH. The other of which gave us a VDS value that was greater than VGS minus VTH. And because triode region operation occurs when VDS is less than VGS minus VTH, we had to go with a smaller value of VDS. And then we were able to use those two values to determine our DC operating point of our circuit. Just a second, please. Oh, crap, that's not what I wanted to do.
Why are the values equal? Saturation, priority, and so forth. Like VGS is 1.147, saturated region is 1.147.
Sorry, let me, so you're saying here, we solved it and we got 1.147.
And then we'll solve it.
And then up here, we got just the value of the resistors that happen to be chosen for the circuit. That's literally it. Yeah, I can't think of any other reason other than the numbers that I happen to choose worked out that way. All right, so Julia.
I was gonna ask if VDS is equal to VGS minus VTH. Do we ever get a reset that for your, if so, like, if we use-
So when VDS is equal to when VDS is equal to VGS minus VTH, we say that it's on the edge of saturation. Yeah. Will I give you anything like that? Probably not intentionally. Will you ever experience something like that? Probably at some point. So let's talk about that for just a moment, okay? When we were dealing with BJT circuits, being at the edge of the forward active region or the edge of saturation really didn't mean a whole hell of a lot. Because in soft saturation, the device behaved effectively the exact same way as it did in the forward active mode. So as long as we didn't operate to where our collector base junction was like 0.4 volts or larger, or excuse me, our collector base voltage was like 0.4 volts or larger, we were pretty okay. Here, we don't have that luxury. As soon as we push our device out of the saturation region, we start that trend where the drain current starts falling down very, very rapidly. Okay. So generally speaking, it's not best practices to bias on the edge of saturation because small variations in power supply voltages or even resistor tolerances can be enough to cause our device to operate not in the region that we were wanting it to. And as we'll find out in a weekish, week and a half, when we're starting to talk about amplifier circuits and all that kind of stuff, the amplifier's ability to convert small signal input voltages into output currents and amplified output voltages is very much dependent on us maintaining our operation in the saturation region. When we get into the triode region, that efficiency factor is much, much smaller. Just like we saw for beta in saturation versus beta in, beta in forward active region versus beta in saturation, we get nice large values. When we're in the active region, we get pretty crappy values in the saturation. Same thing happens here. So let's look at this same circuit again, not this numerical circuit, but let's look at the same circuit again. Our 4 resistor bias network with channel length modulation included, since we know that we probably want to bias this guy at a point that isn't at the edge of saturation. Now, truthfully, a lot of textbooks and things like that will tell you, ignore channel length modulation when you're doing the DC bias point stuff, and then include channel length modulation when you're doing your small signal analysis, which is what we're going to be getting to pretty soon. Okay? But having some means by which to determine your large signal operating point with channel length modulation included can be useful, because for small channel devices, it can be a very large difference in what you think the operating point is if you neglect channel length modulation versus what the actual operating point is. For large channel devices, it actually doesn't particularly matter that much. But for small channel devices, it's very, very critical. So we'll take the 10 to 15 minutes to figure it out. All right. I'm not going to bother redrawing the circuit because it's literally the exact same thing. But with channel length modulation included, we know that our drain current equation changes slightly. We're going to have 1/2 mu n C ox W over L VGS minus VTH quantity squared 1 plus lambda VDS, or 1/2 Kn VGS minus VTH quantity squared 1 plus lambda VDS. So if we apply Kirchhoff's current law, Kirchhoff's voltage law to the bottom loop of our circuit. So this is effectively just the exact same VGS relationship we had in triode region. We're just going to use the different value of ID. We get VGS is equal to VG minus ID RS, which becomes VDD times R2 over R1 plus R2 minus 1/2 Kn RS VGS minus VTH squared 1 plus lambda VDS. We apply KVL to the right-hand side. We can solve for VDS as minus RD plus RS times ID. So this becomes VDD minus 1/2 Kn RD plus RS VGS minus VTH squared 1 plus lambda VDS. And we now have, sorry, this should be equation 1 and equation 2. All right. So we have another equation 2 unknown system, where in this case, we're going to have a second order relationship with VGS, a first order relationship with VDS in both cases. So technically there's going to be 2 solutions. Only one solution will have a positive value for VGS. That's the right one. So you simply solve this system and then plug in whatever you get for VGS and VDS back into this equation up here, and you have your DC operating point. Okay. Do I need to develop new equations for triode region operation if channel length modulation is included? Pretty sure this is the second time I've asked you guys that. The answer is no. Right? Channel length modulation effects are only occur in saturation region because we're making our channel more and more pinched off, which only occurs at saturation. On the triode, since we don't have pinch off, it is literally impossible for us to have channel length modulation effects. So if we find that our DC operating point here does not satisfy the relationship where VDS is greater than or equal to VGS minus VTH, which is possible, we would just use the exact same triode region equations that we developed a couple of minutes ago. They are valid for all operational modes here. Okay. All right, there is another biasing circuit called the self-bias circuit, but we can't get through enough of it in 8 minutes to make it worth our time. So we'll start off with that on Wednesday. So my goal before class on Wednesday is to upload a homework set on using these DC bias circuits and all that kind of good stuff. The homework set will include at least one self-biasing problem, but it will be due, let's say if today's Monday, I'm going to try to get it up tomorrow. Let's make it due next Monday so that you'll have plenty of time to work through that problem and all that kind of good stuff. I will also endeavor to put up something with your theory questions from your first exam, and I'll put it in the exam 1 folder and call it a bonus assignment or something like that. Like I said before, you'll be expected to redo the theory questions of your exam, providing an answer that isn't simply which of the 4 choices or whatever is correct, but explaining why the correct answer is correct, using a paragraph supported by notes, theory, etc. Sound good? All right, see you guys on Wednesday.